All right, so this is our first extended exercise in translating English sentences into predicate logic. This isn't going to make any sense to you if you haven't already studied the screencast and the corresponding parts of the book where we learn how to use variables and names and quantifiers. So make sure you've done that before you attempt to follow along here. Okay, so number one says Bob is a tycoon. You should recognize here that Bob is clearly a name of an individual, in this case, presumably a person. And tycoon is a property. We talk about things that are tycoons. So it's a property which we will characterize as a predicate. And so the convention in predicate logic is always to write the predicate first. So T, and we always write the name as a lowercase letter. So capital T, little b in predicate logic says Bob is a tycoon. When we look at a sentence like tycoons are greedy, what you'll notice here is there is no name. There's no specific entity or thing that is being said to be greedy. What we have here is two predicates, tycoon, tycoonness, being a tycoon, and greedy, being greedy. So it's relating these two predicates together. And essentially, this can only mean one of two things. It means that either some tycoons are greedy or all tycoons are greedy. And in predicate logic, we're always going to adopt the strong interpretation here that it's saying all tycoons are greedy, even though in English, those are actually fairly rare remarks when we're saying absolutely all things with one property have this other property. So how do we say all tycoons are greedy? Well, here we use the universal quantifier for all x. Right? Anytime you introduce a quantifier, there has to be some associated variable. So all tycoons are greedy says for all x, if it's a tycoon, then it's greedy. Okay? So tycoons are greedy says for all x. Make sure you read along with me on this and make sure you're able to read these in this way. For all x, right? If it's a tycoon, then it's greedy. Now, notice that if you had tried something else like and, this says for all x, x is a tycoon and x is greedy. What does that mean? Well, that means that everything in the universe is a greedy tycoon. The fact that that's false isn't the issue because a lot of these sentences might be false. But it seems it's not what's being asserted here. What's being asserted here is that if something happens to be a tycoon, then it's greedy. You should be able to see that it's not saying that if it's greedy, it's a tycoon either, right? And so this is the sort of standard approach to translating this categorical proposition of this form. Now, there is, as we mentioned in the screencast, always an existentially quantified proposition that's logically equivalent to this. And always to get at that equivalence, you're going to involve negation. So when we say tycoons are greedy, all tycoons are greedy, we're saying that it's not the case that there's something that's a non-greedy tycoon. So that's a little bit more complicated. But if you wanted to use the existential here, you would say it's not the case that there exists an X such that X is a tycoon and not greedy, right? So intuitively, these two are logically equivalent, and later on, when we have our proof apparatus, we'll be able to demonstrate that. So Bob is a greedy tycoon. Well, here again we have two properties, and now we have the name Bob. So what does Bob is a greedy tycoon say? Well, in predicate logic, this says Bob has two distinct properties. Bob is greedy and Bob is a tycoon. So Bob is greedy, big G, little b, and Bob is a tycoon. Now you know that that we have a rule of commutation that says that any conjunction is logically equivalent. A and B is logically equivalent to B and A. So if you had chosen to write it like that, you know those are logically equivalent, and so you know that would have been fine as well. Okay, so if Bob is a tycoon, then Bob is greedy. This is one that you can pretty much read right off the English, right? If Bob is a tycoon, then Bob is greedy. Okay? So some tycoons are not greedy. Some tycoons are not greedy says there are things that are tycoons and they're not greedy. If you wanted to put this into an English sentence that was a little bit closer to predicate logic, you'd say there is something that is a tycoon and it is not greedy. And so that would translate quite naturally into there exists an X such that X is a tycoon and X is not greedy. Okay? So one very common mistake, as we've mentioned in the screencast, is to translate this statement using a conditional. Now, why is this a mistake? Well, the easiest way to actually remember this is to just say this and to notice that intuitively it's not really even clear what's being said here. So there is something that is a tycoon and it is not greedy. Does not translate into there exists an X such that if it's a tycoon, then it's not greedy. Okay, so some tycoons are not greedy. So what does this say? Some tycoons are not greedy says that there are some things, some X's, that are tycoons and they are not greedy. So if we wanted to write this down in English, that's a little bit closer to the predicate logic, we could say there is a tycoon, there is something that is a tycoon and not greedy. Okay, so that translates pretty naturally into there exists an X such that X is a tycoon and it's not the case that X is greedy. Now, there is a very common mistranslation, which we've mentioned already on the screencast, of this sort of statement, and you need to make sure you avoid it. This is it, where the conditional is substituted for the conjunction. So why is this wrong? Well, the easiest way to remember this is really at the intuitive level, and just think about what we've written here in this second woof. This is a woof, by the way. It's fine on its own. Read it in English. There exists something such that if it's a tycoon, then it's not greedy. It's not really clear what that means. In other words, what does it really mean to say that there is something such that if it has one property, then it has another property? That does actually mean something, but it's a very unusual statement compared to what 5 actually says, just that there are some tycoons that are not greedy. And a more technical and really more accurate way of understanding why this is not an acceptable translation is to think about the conditional and the truth table for the conditional, and remember that conditionals are true even when their antecedents are false. You'll remember that. If P then Q is true even when not P is false. So imagine a world where there are no tycoons. Well, so there are no tycoons in this world, but you know somebody, say Bob, and you want to say about Bob that, well, if Bob were a tycoon, he wouldn't be greedy, okay? So that would be a way of modeling this particular formula, okay? If it's true of Bob, right, if it's true of Bob that if he were a tycoon, then he wouldn't be greedy, then this whole statement would be true. There exists something that if it's a tycoon, then it's not greedy. But remember, we stipulated that there are no tycoons in this world. So this is a statement that is true even if there are no tycoons. Okay, there exists an X such that if it's a tycoon, then it's not greedy. It's true even if there are no tycoons at all. And if you go back to the original statement, some tycoons are not greedy, that is not a statement that's true if there are no tycoons. Some tycoons are not greedy asserts that there are tycoons. So that's a longer explanation, and one that some of you will probably find irritating. But the easy way to avoid these mistranslations is actually just to remember that there aren't too many English sentences. There are some, but there aren't too many English sentences where you would translate them into a conditional where the operator that's binding over the whole conditional, that's ranging over the whole conditional, is the existential. Okay, there are no non-greedy tycoons. So misspelling there. There are no non-greedy tycoons. What does that say? Well, what you might say, and you would correctly say, is that there are no non-greedy tycoons is just another way of saying that all tycoons are greedy. So you could just say says for all X, just like before, if X is a tycoon, then X is greedy, and that would be a legitimate translation. But if you wanted to capture it with all the negations involved in 6, there are no non-greedy tycoons, you could, again, put it through an English translation closer to the predicate logic. There are no non-greedy tycoons. There does not exist an X such that it is a tycoon and not greedy, or not greedy and a tycoon. So there does not exist an X. It's not the case that there exists an X such that X is a tycoon, and it's not the case that X is greedy. Okay? So there does not exist an X so there are no non-greedy tycoons. It's not the case that there is something such that it's a tycoon and it's not greedy. Okay, so only tycoons are greedy. If you'll remember how only works at the propositional logic level, only tycoons are greedy. It's telling us that not that if something's a tycoon then it's greedy, but rather if something is greedy, then it is a tycoon, right? So for all X, if X is greedy, then X is a tycoon. All right, Eliza hates Gerald. Well, here we are into what we call relational predicates. Hates is a predicate, but it's one that relates to things together. So there's two names here, Eliza and Gerald, and what you've learned is that the way that we represent relations like these in predicate logic are by writing the predicate first and then the two names afterwards in the order that reflects their relation in the English sentence. So this is to be read as Eliza hates Gerald, where hates is written in front rather than in the English where it's written between the two names. Eliza hates Gerald, who is a greedy tycoon. Well, we still have Eliza hates Gerald, right? But we're just adding the knowledge that Gerald is a greedy tycoon. So the who is just represented as a conjunction. Eliza hates Gerald, and Gerald, by the way, is a greedy tycoon. So how do we say that? Well, we already have said that sort of thing above. Gerald is greedy, so little g, big G, Gerald is greedy, and Gerald is a tycoon. Okay, so Eliza hates Gerald, and Gerald is a greedy tycoon. Okay, no tycoon hates itself. This is just sounds a little odd, but it's a little tricky at first, but it's a trick you soon learn. So no tycoon hates itself. Well, if we were going to say that Bob hates himself, we would actually just write Bob hates Bob, like that, right? And if we wanted to say Bob does not hate himself, we would just negate it. So it's not the case that Bob hates Bob. So this is going to tell you that if you're going to generalize this and talk about things that hate themselves, you're just going to have the same variable in for both instances of the constant. So no tycoon hates itself. What does this mean? Well, there's two ways you could say it. You could say for all x, it's not the case that x hates x. Or you could say it's not the case that there exists an x such that x hates x. These also just turn out to be logically equivalent expressions, something we'll be able to prove later. So no tycoon hates itself. For all x, it's not the case that x hates x, or it's not the case that there exists an x such that x hates x. The thing I'll point out is that we'll formalize this later, but you'll notice that I have not put parentheses here, okay? That's correct. That's not required. We do not, it's not only not required, but it's not correct to do it. We don't put parentheses immediately before the corresponding predicate and variable, okay? So just like this is not a woof, okay? We don't put parentheses there. We also don't put parentheses there, or there, or there, right? These are all woofs without parentheses, okay? Let's just get rid of these for now. Make it clear that those are the logically equivalent expressions. Okay, God is not a tycoon. Well, God here is being used as a name. This doesn't say gods, which would be a property, are not tycoons, but God is not a tycoon. So as soon as you recognize that, you've got, that would say God is a tycoon, and this would say God is not a tycoon. Okay, some tycoons are not happy. Some tycoons are not happy. Hopefully this is becoming a little bit natural to you now. Some tycoons are not happy. There exists an X such that X is a tycoon, and it's not the case that X is happy. Or, if you wanted to, you could say it's not the case that for all X, if X is a tycoon, then X is happy. Okay? So some tycoons are not happy. There is something that's a tycoon and not happy, or it's not the case that everything for all X, it's not the case that for all X, if it's a tycoon, then it is happy. Why? Because there's at least one tycoon that's not happy. Bob loves Alfred. Well, here we just have the predicate loves Bob's Alfred. That's easy. But that might tempt you to do 14 incorrectly. And so 14 takes us to another level, and you want to pay particular attention to this one. So what would be wrong? Ask yourself, what would be wrong with saying HDC? What's wrong with that? Well, what's wrong is that dogs and cats are not names of specific things. You could have a dog that was named dog, and you could have a cat that was named cat. But in that case, it would say something like dog hates cat, where those are being used as names of specific animals. But dogs hate cats can't be translated in this way because dog is actually a property. There's being a dog or there's being a cat, right? So those are both properties. So how are we going to deal with this? Dogs hate cats. Well, this is a situation where, our first situation where we're going to involve two quantifiers in a row. So what this says is that for all X and for all Y, and I notice I use the word and, but there's no and written there. So for all X, for all Y, if X is a dog and Y is a cat, then what do we know? So for all X and for all Y, if X is a dog and Y is a cat, then X hates Y, right? So X, Y, and X hating Y. So again, read it. For all X and for all Y, if X is a dog and Y is a cat, then X hates Y. If I change the order here, for all X and for all Y, if X is a dog and Y is a cat, then Y hates X. That would say cats hate dogs. Okay? So that takes us just to another level of comprehension where we realize that quantifiers can be stacked up, and we can introduce more than one variable, and we can relate those variables together. So here what we're being given is a relation between one kind of thing, which is a dog that has the property of being bad, so bad dogs hating another kind of thing, which is something having the property of being a person. Okay, so again, we're going to have two quantifiers here. So we'll say for all X and for all Y, if X is a bad dog, so how are we going to say if X is a bad dog? Well, X is bad and X is a dog. So for all X and for all, if X is bad and X is a dog, and what's Y? Well, Y is supposed to be a person, right? So what this says so far is for all X and for all Y, if X is bad and X is a dog and Y is a person, then what do we know? Well, again, we know that X hates Y. Now, when you get to this level of complication, there's even more different acceptable ways to do things, and I'll just point this out to you at the risk of confusing you. Now, let me just rewrite it here. Now, if you'll notice that we have this rule that you don't have a woof if you have variables that aren't being bound by quantifiers. So we definitely have to have the universal quantifier for the x before these x's, or they wouldn't be bound by the quantifier. But we don't have to actually have the y here yet. We could insert it right here if we wanted to and change this so that it's a woof. So the first thing to notice then is if we move our quantifier, the universal quantifier in for the y, we still have a woof because the x's are all being bound by the universal quantifier for x being completely outside the entire formula, and the y's, which don't occur until here, are being bound by the universal quantifier for the y. So this is a woof. Now, having said it's a woof, that doesn't mean that it's a correct translation of bad dogs hate people. Is it? Well, let's read it. For all x, x is bad, and x is a dog. And for all y, if y is a person, then x hates y. That's kind of close, but it's not right because this literally says everything is a bad dog. We don't want it to say that everything is a bad dog. We want it to say that if something's a bad dog, then if it's a person, then x hates y. Okay, so now what it says is for all x, if x is bad and x is a dog, then for all y, if y is a person, then x hates y. So bad dogs hate people for all x, and for all y, if x is bad and x is a dog and y is a person, then x hates y. Or alternatively, for all x, if x is bad and x is a dog, then for all y, if y is a person, then x hates y. Okay, so intuitively those two are logically equivalent, and later on, as I've said, we'll be able to prove that. So getting back to 15, only bad dogs hate people. Well, what's that saying? Well, we know how only works. Only bad dogs hate people means that if something hates people, then it's a bad dog, right? If something, or if anything, hates people, then it is a bad dog. So again, we're going to have the two quantifiers for all x and for all y. And then we can say if x is a person and it's hated by y and y hates x, so for all x and for all y, if x is a person and y hates x, then what do you know? Well, you know that's a bad dog. So that's a bad, so that means that y is the one that's hating x in this case. So that means that we know that y is a dog and that y is bad. So for all x and for all y, if x is a person and y hates that thing, that person, x, then y is a dog and y is bad. Okay, so those are tricky. We'll get to those being kind of familiar within the next week, but let's see if we can go ahead and finish these off that are a little bit more complicated. So every troll is under some bridge. Well, we've got, so it looks like every is going to bring us within the realm of the universal quantifier, and it looks like some, there is some bridge under which the troll's under. It sounds like that's going to be the existential quantifier. So every troll is tells us something like this: for all x, if x is a troll, then there is a y such that y is a bridge and x is under y. Okay? So how would we translate that into predicate logic? Well, for all x, if x is a troll, then there exists a y such that y is a bridge and under x, y. So for all x, if x is a troll, then there is some bridge. There exists a y such that y is a bridge, and that troll x is under that y. Notice again how it might have been tempting to use the conditional here, but we said earlier that's hardly ever going to be the appropriate translation. The existential is ranging over this whole sentence, so the conditional would not be the appropriate interpretation here, just as before. Now, you'll notice that what I did here in doing this one was to distribute the existential inside. And just as before, we could have, although I've done this in the reverse order, we could have had the existential on the outside. So for translation purposes, it's often more intuitive to put the quantifier on the inside. However, you will still have a woof if you have the a woof where the quantifier is on the inside. You will still have a woof if you just take the ones on the inside and move them to the outside. So you can now, if you like, move this quantifier. It has to stay in the same order. You may, if the existential in this case is in front of the universal, and when you move it back out, it still has to stay in front of the universal. But this way of redistributing the quantifier actually does not change the meaning at all. Sentences where the quantifiers are all lined up on the outside are called normal form. They're not better, they're just a sort of standard way of writing things. And these two sentences actually mean the same thing, which you can kind of test intuitively. Our original one, for all x, if x is a troll, then there exists a y such that y is a bridge and x is under y. Alternatively, for all x, there exists a y such that if x is a troll, then y is a bridge and x is under y. You notice this one rolls off the tongue a little easier. It corresponds more obviously to our English sentence, but this one is also a correct translation. Alfred only loves himself is a tricky one, and we'll actually have a far better way of writing this in a couple of weeks when we introduce a interesting relation called identity, which is essentially just the relation of equals that we don't have right now. But if you were going to write something like this now, first of all, just ask yourself, how would you write Alfred loves himself? And we've already experienced something like that. You just write Alfred loves Alfred, and that helps you to remember that there's going to be a variable, the same variable that's going to be substituted for Alfred both times. So how could we write out Alfred only loves himself in an English sentence that's somewhat similar to the predicate logic version? Well, Alfred only loves himself says that if Alfred loves something or someone. If Alfred loves someone, then it's Alfred, right? So for all X, if Alfred loves X, then X is Alfred. So we know how to write the first part for all X. If Alfred loves X, right? For all X, if Alfred loves X, then how would we write X is Alfred? Well, the is here actually means is identical to, right? It doesn't mean that, I mean, it could mean this, but it's a very odd way of interpreting it, that X has the property of Alfredness, right? We don't think of Alfred as being a property. We think of it as being a name in predicate logic. So if we're going to say X is Alfred, we'd really have to introduce a relation like E for equals. So for all X, if Alfred loves X, then X equals Alfred. And that's a particular relation that's actually going to be of a great deal of interest to us, so much so that we will eventually be incorporating the equal sign from math, and we'll be able to do specific proofs involving it. But for now, this is really the only thing we could say where E equals to get our E means, right? Equals. So that would be a good shot at that. Something loves something. How do we say that? Well, there is an X and there is a Y such that X loves Y, right? Very important to introduce two variables here, because if we just used one X, then we'd be saying something loves itself. Or if we just used a Y and not an X, we'd be saying something loves itself. So since there's two variables, there has to be two quantifiers. So there exists an X and there exists a Y such that loves X, Y, okay? There is an X and there is a Y such that X loves Y. Now, we could also have written there exists a Y and there exists an X such that X loves Y, or that Y loves X, because there aren't any specific things being identified here. These will all mean the same thing in this case. What about something loves everything, though? How would we write? Well, something loves everything says there is something that loves everything. So there exists an X that loves everything. So there exists an X such that for all Y, X loves Y. Okay, so there is something that loves everything. There is an X such that for all Y, X loves Y. Now, what's interesting and also very important to notice here is that now we don't have, because we have two different kinds of quantifiers, we don't have the same ability to just randomly switch the order of these quantifiers or the order of the variables. So suppose we did. Suppose we said for all Y there exists an X such that X loves Y. One way of switching, so we switched the order of the quantifiers. So what does this say now? This says for all Y there is some X such that X loves Y. So for everything, there is something. Okay, for everything, there is something such that X loves that thing. So this actually says in English, everything is loved by something. for all y, there exists an x such that x loves that y. So there's a very big difference, right, between saying there is some one thing that loves everything and saying everything has something that loves it. Now, these could both be true. They're not contradicting each other. But when we say there is something that loves everything, then we're saying there is some one thing that loves everything. But this is saying that everything has something that loves it. And in that case, it could be many different things, right? As long as there is nobody who's unloved, it could be that they're loved by very different things. And number 20 is, again, very similar sounding, but also different than either of the above, right? This says there is something, there is some one thing that everything loves. So there is an x such that for all y, y loves x, right? So there exists an x such that for all y, y loves x. So there is something that everything loves. There exists an x such that for all y, y loves x. And again, we could experiment with changing the order. Let's, for example, this time not change the order of the quantifiers, but change the order of the variables. So why don't we ask what it would mean if we said this? Well, actually, that isn't a very interesting thing for us to do, is it? Because there exists an x such that for all y, x loves y, means there is something that loves everything, right? There exists an x such that for all y, x loves y, which is just what we had originally said up here, okay? Let me, in order to make sure people don't get the wrong idea, make it clear that this is that, okay? And this one was just what we dealt with in 19 already. So maybe we, let's go ahead and actually do fool with the order of the quantifiers, right? So what if we said this instead? So for all y, there exists an x such that y loves x. Is telling us that everything has something that it loves. So this says everyone loves, or everything loves something. Okay, so again, we have this interesting relationship. There is something that everything loves. The first one, there is something that everything loves, tells us that there is an x. There is some one thing that everyone loves. There is something that is loved by everything. But for all y, there exists an x such that y loves x. It's just telling us that everything has something that it loves. And again, it doesn't have to be the same thing in each case. So these are tricky. They're actually really worth working on, trying to understand, because it gives you a real sense of just how subtle and expressive these quantifiers can be. Okay, so that was the end of the first worksheet, and now I've given you another one, a longer one to work on. I'm not trying to give you the impression these are easy. They're not. It takes a while to develop your intuitions, and the way you do that is by doing a whole bunch of them and checking to see how they work out. Okay, so do those for the next class, the next sheet for the next class meeting, and we'll see if we can solidify our understanding of these a bit better.